Assalamu alaikum, ladies and gentlemen. Welcome back to another live stream. So, after a very long while in the barren lands of C++, we're back to Rust. We're back to my most favorite language. Cause like yesterday, I was struggling with my C++ Vulkan engine. I had some sig faults on release mode. It wasn't apparent in debug mode pretty much, and I tried to debug it, but to no avail. I used sanitizers. I used literally everything I could. But it was kind of like, I mean, if I probably wasted more time on it, maybe I could figure out a solution, but I was just contemplating at that point, like, what the heck, how it would be like debugging a bigger engine. And then I realized how really far, I mean, I knew what Rust was actually handling for me, but it became even more apparent, like with this little accident. All right, live. Okay, so let's see, public. All right, cool. So this is what we had. It was just like two streams. In fact, you could watch it, like you could watch the whole making of the game engine. It's just a little thing, just a little Vulkan render pretty much. In fact, it's in GitHub right now. So as you can see, you could like launch multiple windows fine. It's using Vulkan SDL3 and like SDL render and so on. Please join my Discord server and so we can get notified of stuff. But yeah, other than that, you can find the link in, hold on, let me actually grab the chat, by the way, about the chat. Let's go. So you can find this C++ code. Hello Berisa, welcome to live stream. How's it going? All right, so you can find the C++ code if you want it in my GitHub. Let me see. It's using the latest modern C++. I kind of found myself trying so bad to replicate Rust in C++ using the latest standard. And in fact, C++, like the latest C++, is really adopting a lot of the features of Rust and more modern languages. But the real problem is, it's so freaking ugly and out of place. Why? Because, well, C++ have to basically keep, backward compatibility and so on. So I even kind of cleaned it up a bit using a lot of stuff pretty much. But yeah, also in this video, probably going to be using dynamic rendering, of course, Vulkan 1.4 versus scriptures and other stuff. There is, we're not going to be using Vulkan memory allocator VMA. We're going to be using a pure Rust allocator for Vulkan, which is also fine, which is also good. Otherwise, yes, we're gonna try to do the same multi-window, multi-device rendering our engine architecture. Other than that, I'm not sure about the runtime share compilation. Maybe we could try that out. I haven't like programmed in Rust for a while now, for a very long while. I try to stick to C++, but like yesterday was my last straw with C++, honestly. But yeah, it's like, it's not just that. It's also the fact that I was looking into, for example, the libraries of C++, like let's say for networking and asynchronous programming. And the best I could find really is Boost ASIO, and that was nowhere near close as Rust Tokyo and Serde for serialization, deserialization, and a whole bunch of other stuff. But yeah, either way, we're done pretty much here. So yeah, this is the code. You can find it on GitHub, and pretty much there is like an application here, as you can see. And then there's the engine code right here. Of course, it's using CMake and VC package and so on. It's like have all the freaking flags of Clang, which is pretty cool. Like, let's say, for example, GPU, CPP. This is the code that a lot of the code is right in this file, pretty much. But yeah, if you really want that, you can check it out. Other than that, let's get straight into Rust. I just basically installed Rust Rover. I'm not sure how much Rust tooling have improved since I've left, but I guess we'll find out today. Live, so yeah. Alright, so let's create a new project, and well, what should we call it? Let's call it Rust Coda Chaco Engine. Rust, I guess Rusty Coda Chaco, Rust Coda Chaco Engine, fine. Let's create this. And I don't have to choose a compiler and like a build generator and a meta build generator and a build system and so on. I don't. Or -rs. Actually, thank you so much for that idea. I forgot about that completely. Alright, let's use -rs. That's good. I haven't been in the Rust land for a very long while, so I forgot about those conventions. Now the amazing thing about Rust is that we have conventions for everything and we use the same tooling. It's not like C++ where like someone is using VC package, other is using Meson and CMake and other. So there's just a bunch of crap. But anyways, so here we get a binary application. Now of course Rust is not perfect, you know, there's the borrow checker and the in-safe crap and so on, but well, nothing is perfect, I guess. Alright, let's just create this Coda Chaco engine -rs. Yeah, let's create this. Perfect. Now let's see what we got. I always like my layout to be like this. And honestly, I'm gonna save it really. You could go to, where is it called? And also I'm gonna put this here to, what the heck? And I'm gonna put this here. Other than that, we could come here now and go to, window layouts and save current layout. Actually go here and save changes to save this layout. So you don't have to like change it every time. It used to drive me crazy. And honestly, let's do it this way. Layouts, custom, save changes. Alright, cool. Other than that, we should be good. Let's check this out. Cargo check, run external lint in order to fly. That's good. We're going to be using the default channel. rustfmt, great. We're going to make sure that the save actions is formatting. Actions on save, reformat, optimize, rearrange code, run code cleanup. Let's go. Perfect, and this is our first hello world in Rust. So in Rust we have two kinds of options here. We could either use Volcano, which is a safe wrapper around Vulkan in Rust, right, around the raw binding, and we have Ash, which is the raw in safe binding. And while Volcano is pretty cool, like they even have a task graph, they have their own allocators, they even support, you know, ray tracing and all sorts of cool stuff, and even async kind of to some degree. But to be honest with you, I don't want to learn another API. Like the raw binding is like truly just one-to-one, you know, it's literally the same thing, and like it's complete and there's no chance for bugs in the code or something. While this one is like more handmade, but it's much nicer to use, especially if you're just starting out. But since I'm really used to the Vulkan raw API anyways, I'm just gonna go with this one really. And also the other thing is that Volcano does add a bit of overhead for validation and so on. It does save your ass in terms of validation to make sure you're using the API right. But honestly, we have the validation layer for that. But either way, let's just go with Ash really. Alright, it's the safe wrapper kind of. kind of. Well, that is true, yeah. You got a point, right. Anyways, let's see. I haven't done this for a really long while right now, so we're gonna see how it goes. Alright, so first of all, you don't have to deal with CMake here. rustfmt enabled by default for whole file. Begin with Rust rover, etc. Okay, cool. Alright, now, okay, cool. So here you don't have any CMake or any crap like that. You just say cargo add and say which library you want to add. In this case, it's Ash. Now, of course, Ash is not the only one we're gonna need. And the other thing that we're gonna need, and since it's very easy to like add libraries in Rust, like you could see that the community really try to use, like they're together essentially, they're united. Like people make libraries and other people depend on those libraries and they build upon them and so on. And like in C++, where like everybody's doing their own thing and like everybody's doing everything from scratch, in Rust, since we have a very good unified and simple build and package manager, right? So that's basically the case. All right, other than that, let's see what we're gonna need next. We're also gonna need some windowing, of course, windowing stuff. So we're definitely gonna need winit, which is like the raw Rust windowing stuff, kind of like SDL3 in C++, but yeah, to some degree. Either way, let's say winit Rust. Here we go, so this one. All right, that's cool. So let's try to add that too. So cargo add winit. And there we go. For the math library, there is quite a lot of options. There's in algebra. This one is quite big. It's not big, like complex. Kind of like Egan in C++. It's like if you're doing sciencey stuff, then you probably want this. And there's the easier one, kind of like GLM. In Rust, it's kind of like GLAM Rust. This one is like GLM in C++, so yeah, we're gonna go with this one. There's some other options, but we're not gonna go into that. So cargo add GLAM. And of course, every single one of them have these features that we may need later on, like bytemuck and so on. But other than that, so every dependency you add, it would be added to your cargo or toml here, and that's basically it. Now, I think let's try to start this. So first of all, we need to make a window. How are we gonna make a window? Well, I don't know. I guess we'll find out. And this is what's great about these live streams. You could really see me how I figure out stuff. So let's go to the examples pretty much, and let's just check out some example real quick. I don't know, this window.rs maybe. All right, cool. Let's see. And they're using tracing. Oh yeah, I just remembered tracing. All right, tracing, and they're using this one for the web platform. All right, let's just start with winit stuff first of all. Right, so the first thing first we're gonna need to create is an event loop. Now in SDL, you usually just like, you know, make your own while loop and just check if we need to exit and then exit yourself. In Rust though, you just create the event loop like this. There we go, event loop new. Now in Rust, we don't have exceptions, we have results types, right? And you could either just say like the inwrap for everything and then we just crash if there is an error, right? Otherwise, you could just say this instead, result box dine error. You don't really need to understand what this is about, but essentially it would allow us to return any kind of error type, you know. It's dynamic. It's like, I don't know what to say. It's basically dynamic dispatch, right? Other than that, instead of this, you could also add anyhow to make it a little bit nicer and more convenient to return any kind of error to your function. So you could easily whip up. Now, if you're making an actual library, you do want to make an enum of all the possible errors. But since we're just making an executable and we don't really care too much about the errors, we're just going to use anyhow. So here you could basically just say anyhow result. And there we go. What's up? Anyhow, result. And we're just gonna say okay. All right, so just return. So here in Rust, we don't have like return and do that. Like if the expression is at the end, you don't have to return it. You just type it in, right? And right now, as you can see, I could just make this right after the result, and then it's gonna unwrap it for me. It's not like, you know, C++, if you have, let's say, an optional, every time you have to say, you know, this, the option, right, to unwrap it. No, here we just unwrap it once and done. If there's an error, it would return from this function with the error. Anyways, that's just a little bit of stuff there. Now we're gonna event loops run app default. Okay. So let's see, event loop run app. So here we need some sort of an app here. And let's see what we got. So app, right? And of course you're gonna need an app, right? Whoops. I'm still in my C++ brain right now. Wait. So let app. Oh, wait, where is the app here? Oh, they just created the default app. Okay, cool. So let's just do it ourselves too. Oh my god, it's gonna take me a while to adapt back to Rust. So here we're gonna impl default for app, and we could just implement members. Okay, and here we could return a new app, right? Let's see. I really like how Rust really encouraged documenting well from the start. Yeah, so like really that's one of the biggest things too, is that like every single library, they have the same exact documentation format. You don't like in C++, some libraries put the documentation in GitHub, some put them in a dedicated website, some don't put any documentation, some put them in the README. It's such a mess. But here in Rust, like you literally always have the same thing, you know. But yeah, all right, let me see how Winit is doing this stuff right now. Implement application handler, but like where's the default? Oh, they just derived the default. So instead of implementing it ourselves, if all our fields implement defaults, we could just use this kind of derive thing to derive defaults. So it would implement, the compiler would implement defaults for us essentially, but not like in the C++ template way, which is bloats up the compile time. I mean, here also it does, but it's much more organized than C++ mass. Because like the template stuff of C++ is just kind of like bolted in into the original C++ that didn't have templates, right? But in Rust, it like was created from the start with this kind of way, so it's much more mature in that sense. But either way. So right now we got a window option box dyn window. Why the heck they did it this way? That's interesting. I don't think you really need that. I mean, I guess we'll find out. So when it really does change a lot actually from, but we'll see. So we're gonna import Winit window here, can we? Oh, well, they did change it a lot apparently. They're using this, so apparently right now it's a trait for some reason. That's weird. But okay, let's just follow through. Expected trait found struct window. I don't know what the heck is this. Wait, where the window is coming from here? It's coming from Winit window. So what's up? Wait, let me make sure I'm in the right version, by the way. So which version I am? Because here this is master, right? So this is the main, and this always trips me up. So 0.13.12. Let's go to 0.13.12, 30.12, and let's see what we got here. And let's see, where is it? Application. Okay, so they have Windows hash map window ID, Windows state. Let's see where this Windows state is inside. What is it? Windows state, here we go. So arc window, ME surface. Interesting. Cursor grab, zoom, rotated, panned. Well, let's see. So why did this didn't work? Let me import this. Oh, so the trait default is not implemented for window. Okay. Sure, that makes... Oh yeah. To actually implement default, we need option. But why would we even need that? That's weird. But anyways, let's just see what we could do here. So fnu and let window is equal to window. I guess how do you create a window? I think maybe you grab it from the event loop. Let's see. How about we go to the documentation maybe? Because this is a bit of a complex example, honestly. Let's check out when it's documentation, because it did change a lot from last time I used it. Then you create a window with create window, where this create window is in the active event loop. But how do I get the active event loop? I get it from resumed function. Okay, I kind of start to remember now. So like we have option here. This is like std optional in C++. Okay, and then we basically need to implement this trait called application handler from winit. And then what else? Well, of course, we're gonna implement it for app. I'm gonna need some time to actually get back into Rust stuff. So we could implement all these functions, and they give us multiple stuff. Like for example, this resumed would tell us when the application would resume, window event, when there is a device event, and so on. All right, let's say okay. And now it generated these two. So the resumed here where we're actually supposed. So let me tell you what's going on here in exactly why it is this way. Because like in Android, you're not supposed to create a window until you get an event, a resumed event from the lifecycle. Maybe also iPhone, I'm not sure, but like, yeah, that's basically the case. And when you get paused event, I believe, or what is it called? Generate implement methods. Suspended, when you get the suspended event, you need to basically remove the window in some sense. Not really the window, but like just the surface. Like if you have a vulkan surface created, then you should destroy it, because like the app would go into the background, right? That's basic, and it would become invalid. So yeah, all right. Okay, fine. Let's see. All right, let's try now to actually create this really. Let's not worry about this suspended for now. For resumed, what we're gonna do, we're gonna say self.window is equal to some event loop dot create window, and here we give it window attributes. And right now, I'm just gonna go with the default. I don't care. Other than that, we're good. And we need a little... Okay, cool. Oh my god, I'm so glad I'm back into Rust. Alright. So here we created a window. Cool. Now what? So here I believe maybe we need to just like... I mean, hold on. Let's derive default. And we can derive default because option derives default, and the default of option is just basically nothing. And that's essentially it. Now what's up? Add expect. Oh yeah, so this could fail. Alright, fine. Can we just redirect it like that? Best stream channel I've ever read. Hello Mucho, welcome to the live stream. Convert to mutable. Alright, cool. So right now we're just kind of figuring out the new changes of Winit live. I haven't programmed in Rust for a while now. Alright, so we created application handler, resumed, and Yeah, that's sick. Now, oh my god, match function. Let's go. When it's plus, exactly, yeah. That's what we're gonna use. Right, so how do you do that again? Window events. Alright. Let's see the documentation. So event handling. Alright. Close requested. Cool. Window event close requested. There we go. And once we get that, what we're supposed to do. Okay, so we say event loop.exit if we want to exit. That's cool. So event loop.exit. And I guess like this, right? Yeah. Alright, that's cool. Is that it? And redraw requested. So in fact, by the way, this kind of design, it kind of felt weird to me before when I just started learning, when it's like, I don't know, years ago. But in fact, it's the cross-platform way, since like every single, like some platforms basically like to takes care of the, or own the event loop, right? So SDL and GFW, for example, didn't account for that at first, though right now, for example, SDL at least added something called the main callbacks, which is basically kind of doing the job of this kind of event loop basically here. Just giving you some, I'm not sure, yeah, I can't connect, interesting. It's the server is down of SDL3 for some reason. Alright, anyways. Cross-platform equal hoax. You can't lock the cursor on Wayland. I mean, it is true. Like, cross-platform really sucks. But to be honest with you, native isn't really that better to some degree. Like, you know, creating a Wayland application from scratch. It's not the easiest. At least X11, it was kind of manageable, although it kind of sucked. But it was manageable. Winterly 2, same thing. Yeah. So, honestly, for example, though, Android and probably Swift, like for iPhone and so on, those actually have some really good native integration stuff, really. Especially Android, I really loved the Kotlin UI. It's really so good. Otherwise, let's just see what we could do here. Can we actually run this now? Let's try. Though I'm not sure, since in Wayland, like, it requires you to like render at least one frame for the window to show up. I'm not sure how did it handle it. But at least in SDL, that was the case. Yeah, I believe so. I mean, here we go. We're getting a when it's window, but it's not showing up, because like in Wayland, it just doesn't show up until you start rendering. Unfortunately, otherwise we're good. And I see there is the cursor warp protocol for that now. Yeah, Wayland stuff is quite interesting. Either way, so we're done, I think, with creating a window, right? Yes. Alright, so what's next? Let's remove some stuff here and let's go back here, I guess. And so how are we gonna do Ash stuff now? Let's see. So for the Ash stuff, well, actually we should basically put it in. Well, we're gonna create like another kind of struct actually called, I don't know, maybe GPU. Yeah, let's call it GPU, and yeah, we're gonna have it here, option GPU. Now the GPU here, I think would basically contain, well, let's check out the documentation here. Where's the documentation? Here we go. Okay, so we need an entry. So first thing we're gonna need is an entry. How do you, oh, ash entry. There you go. This is like the library, so it's Lloyd's the DLL of Vulkan. Next up, we need the instance, pretty much. So the instance is ash instance, right? I can't type today. And then what? Well, of course, we're gonna need, I believe, physical device. Okay, and the device and the queue. We don't have that because it's just a little handle. It's not really an actual Vulkan object, like a dispatchable one at least. Let's import vk, why not? And so we could remove these. Otherwise, so yeah, I believe that's pretty much it. Entry, instance, physical device, device queue. Now let's try to actually, so we're basically gonna implement this. So implement GPU, and we're gonna have a new function here. And yeah, and we basically it would return self. Self basically stands for GPU. You could even say GPU, but like if you change the name, you could just easily change that there, but yeah. Otherwise, we're good, fine. So now, how are we gonna do this? Well, first of all, this should be an insafe function, I believe. And then here we could create an instance, so... well, actually, first of all, entry. So entry is equal to entry Lloyd? Yeah, Lloyd. And well, this would actually return the results. And we're just gonna basically, hello Zappers Live, welcome to the live stream. Alright, so since this returns a result, I want to basically kind of like essentially propagate it back to the caller. Just because I don't have any clue how to handle it here, I don't care about it. So I'm gonna use anyhow result here. And yeah, so what's up? All right, cool. Now what? I think, can we just say unreachable so it doesn't really annoy me? Consider wrapping the function body in a save block. Ayo, what the heck happened? Oh, so I can't even, interesting. So I just have to make an in-save block anyways, apparently. Alright, cool. Now, we got an entry. Next up, we need an instance. So let's make an instance. Do I like create instance? Yep. And then here, or to do. Yeah, unreachable or to do. Yeah, exactly. To do. Let's go with to do. And here, create instance. So vk instance create info, right? And I forgot completely how, is it like default maybe? And then you set stuff here. And then the allocation callbacks, none. Oh yeah, we gotta basically take a reference there. And that's basically it. Now we could set whatever we want here, I believe. So dot application info, enable extension names. Yeah, we're gonna need the required extensions of this current platform. I believe Ash had something for that. Ash window, I believe, or something like that. I don't remember. Yeah, hold on, go back. Ash window, yep. So let's search it up. Let's look it up. Ash window Rust. Well, there's two here. There's this one and there's this one for some reason. Over 1 year ago. Wait, what? Well, I would guess probably this one. Ash dash window. So cargo add. So I'm just gonna copy that. Come here. Boom. And we've just added a library. No CMake got harmed. Perfect. Next up, what we're gonna do here. So we have enumerate required extensions, and we give it a display handle. So here again, another nice thing about the Rust ecosystem, like for example Windows, how C++ handle like window handles, what they do in libraries. You know, they just request you to give them the raw Win32 handle, and like the raw platform handle, which really sucks. It's not cross-platform. In Rust, though, what they did is that they have this library called raw handle, I believe. Yeah, raw window handle. And this library is kind of like just like an interface. Any library that wanna basically, let's say, implement some windowing stuff, some windowing solution, like for example WinIt, SDL3, GLW, etc., bindings and so on, they too simply just implement this library, this raw window handle library, and now anybody else who wanna consume this library, it would just work out with anything. It would work out with SDL directly, it would work out with GFW, anything that implements this interface in some sense. So like in Rust, we have interfaces in libraries. And in fact, this pattern is very cool. We have it for this one, we have it for window handles. And we also have it like, for example, for logging, log Rust. This one is also kind of like an interface, and then you have like login implementations and so on. There's also tracing. This is another login interface, but for asynchronous stuff and so on. But either way, let's go back to business here. So let's see how we could do this. Well, we're gonna need the required extensions right now. Let's see how we're gonna figure this out. Required, enumerate required extensions, and here you give it the display handle. Well, raw display handle. So let's grab the display handle, raw display handle, and we just pass it up here. And basically when it actually goes ahead and actually implemented this raw display handle, so we could just pass it up when we create it. Have you used other distros before CachyOS? Definitely. I used a lot, pretty much. Well, of course, Windows. There's Arch Linux, Manjaro, like the raw Arch Linux, Manjaro, and Endeavor OS just a bit, Ubuntu in the old days. But honestly, CachyOS was like the most seamless. Like you just install it and NVIDIA just works. Also, I tried Fedora. That was also good. Though all of these need some extra stuff to make, you know. Also, I tried, what is it called? What is that? Nix, yeah, NixOS. I also tried NixOS. Pretty much. I like the concept of NixOS, but I couldn't really go with that kind of way. Otherwise, Fedora worked fine as long as you install the NVIDIA drivers. The others kind of had problems, especially back in the day with Wayland and so on. Oh my god. But today, NVIDIA with Wayland is kind of fine. I mean, so far I didn't have any problems, especially with CachyOS NVIDIA drivers. You know, they're installed by default. So if it just detects if you have NVIDIA and it just installs the right drivers for you. So you don't have to bother. And that's basically it. But yeah, though I think for the InSafe function, maybe we could just put it here really. Can we? Is this also InSafe? Well, it's also InSafe. Alright, fine, let's do it like this. And there we go. Now where we were. Okay, cool. So let's actually create a GPU here. So here's how you do it. So self.gpu equal to sum. Well, not event loop. We're gonna say GPU new, and we're gonna give it the raw something that that implements raw display handle. And when it does it for us, so we could just pass in event loop, I believe. Is that right? At least that's what I remember. Hello, Abdurrahman. Welcome to live stream. Consider using result expected. Change type. How do you get the raw? Yeah, I think like this. No? Let's see. Let's see in wrap. What's up? I guess this is deprecated. Use has display handle instead. Hey dude, just passing by. I want to wish a lovely day and a happy coming. Thank you so much, Kevin. Thank you so much. Welcome to the live stream. Okay, so how this would work? Let's try to run this. I believe Rust compiler would give us something about that, maybe. Expected draw display handle. Huh. Found active event loop. How about we do this for now at least, and just pass up the display handle here. Or maybe we need to do it this way? I don't remember. No, hold on, let's go back. Let's try to figure this out. How do you do that? Well, Ash window. Well, actually, let's go to the Ash examples, really. Let's go to the Ash window examples. So let's go back to the repo, and let's check it out. Maybe Ash window, examples, WinRS, let's go. And let's see what we got here. Okay, so you just say the display handle as raw. Alright, fine. The display handle as raw. Is that it? Yep. That's pretty much it. Right. Yep, pretty much. Now let's actually give it this extensions. So enabled extension names, required extensions. Though this needs to be in wrapped because it's a result. And then we pass it up here. Other than that, let's go. What's next is the application info. So vk application info. And how are we gonna do this? Default dot API version. Vk API version. Oh, we don't have 1.4, huh? Why? That's weird. Why there's no... Why there is no Vulkan 1.4 in Ash Rust? Let's see. I mean, let's check the actual repo. Probably there's someone actually talking about it, no? Vulkan 1.4. There we go. Someone... Vulkan 1.4 was announced in December. No urgency, but curious whether Ash is expecting support and how difficult that might be. Okay. Interesting. Interesting. So they don't support Vulkan 1.4 just yet, apparently, but it's fine. We could just use extensions. Other than that, let's see what we have else. So that's pretty much it for the instance. Let's go to the next thing, which is the physical device. So physical device, I'm just gonna pick the first one really, I don't care. Instance enumerate physical device, and we're gonna grab, first of all, we're gonna make it into an iterator, I believe. Yeah, so we consume that iterator, I guess, and then we take the first one. How do we do that? I guess next, right? Yep, next in wrap. But wait, what's up? This returns actually results, so it's in wrap that, I believe. There's some weird thing here though. Wait. So this gives me a vector. Oh, it's an insave function. Insave function, okay. And honestly, let's just grab the first one. As I said, into iter dot next dot in wrap, and there we go. Now we got the physical device. Next up, we need the device to create the device. So the device is it instance.create device? Yep. And here we just need the physical device and vk device create info. Okay. Default dot. Here we enable some extensions. In my case, I only need one extension currently, which is the so are you making a general engine or specifically BPRRT? I'm not sure exactly yet. Right now, I just want to kind of like mess with and learn Vulkan more, and like with the newest Vulkan extensions, I want to make it as ergonomic as possible and modern as possible. Like I want to, you know, experiment with newer extensions and so on, and kind of make an API. I'm not sure exactly if I'm gonna go just with a renderer or an engine, but we'll see how it goes, basically. Pretty much, unless if you guys have any kind of like suggestions. Otherwise, so I need to know where I can grab the names of the extensions though. Like swap chain extensions. I believe maybe no, hash khr swap chain, is that it? Oh yeah, name, here we go. And what's going on here? I guess maybe we need the address of here. And this is in safe too. So let's wrap that. So this function takes 3 parameters, which is the allocation callbacks here, and there we go. And that's basically it. Now what's up with this? Alright, so this takes a slice. The other thing I really hate about C++ is that you're never sure if you're copying stuff or like moving stuff. Like the syntax is everywhere. Either way. Type mismatch expected const. Found that. Expected raw pointer found reference. Can we just grab as BTR maybe? Is that the case? Yep, it is. Perfect. Alright, so we just grab the name, which is a C string, and then we get the pointer from it. Next up, what else we got? The enabled features. So here we're gonna need the q create info. So vkq create info, and here we're gonna go with the default. And well, of course, we're gonna take the address of that. And let's see. Though actually it should be a slice, I believe. Yeah. Lovely. Hello, Block Sumo guys. Welcome to live stream. Alright, so queue priorities and queue family index and push next. So we're gonna need, of course, queue priorities here, and there we go. We only need one queue for now, so. And we're just gonna go with, honestly, with the first one. What distro are you using, if I may ask? I'm using Cache OS, which is an Arch Linux flavored kind of thing. It's based on Arch Linux, by the way. Never mind. All right, cool. So we got the device, and then what else? We need to get the queue now, though. That's actually the blazingly fast OS. Yep, exactly. And now let's see what we got. So let queue is equal to device get queue, I guess. Get device queue, yeah. 0, 0. And again, we need that freaking unsafe crap. Honestly, this unsafe stuff really kind of sucks. I think I'm just gonna make it once and call it a day, really. Will you ever rewrite the engine in Scratch? What do you mean Scratch? In Scratch? Like the... you mean from scratch? If so, yes, I am rewriting it from scratch. Let's see. Alright, well, like this, or what the heck? Oh yeah, to do. So right now we could actually return self, and now I believe we could just change return type method new to GPU. Well, it's not already. What the heck? That's weird. Alright, let's add the missing fields, and there we go. So this is like, you know, C++ initializer list, essentially. And yeah, that's basically it. So, what's going on here? Oh, because, well, what the heck? Wait. Oh, gotcha. I see what happened there. So this should be okay, self. There we go. Alrighty. And we're done with the, I guess, GPU part, maybe? Oh, no need for this one, I believe, and that's basically it, I guess. Right, so if I right now run this just to make sure everything is compiling, and what the heck? Oh, ash entry. And we don't need these in safe everywhere now. Too much noise. Just one unsafe block is enough. Although it's less granular. But yeah. Alright, cool. Alright, what's next? So, well, there's actually a lot to do next. Well, let's start by a command pool at least. Make a command pool and some command buffers, I believe. So let's start there, and honestly, let's grab, we also need a graphics key family index, or honestly, no need for now, I guess. Fine, no need for now. I'll just keep it at 1 queue. And let's basically say now here, let command pool is equal to device.create command pool. And what we need here, we need command pool create info. So command pool create info default dot queue family index. Just gonna keep it as 0 so we can omit it. Other than that, we probably need some flags though. Command pool create flags. And we're gonna go with reset command buffer so we could reset them, I think. And maybe also transient. Vacay Command pool, create flags, transient. Otherwise, this should take a reference actually, and other than that, maybe we just need a semicolon, or do we need something else? Provide the arguments. Okay, so none here for the allocation callbacks, and that's basically it for the command pool. Next up, we need some command buffer. So let's go with allocate. Wait, what the heck? No, device allocate command buffers, and what this takes. Come on, this takes an allocation info. Okay, command buffer allocate info default dot. So command pool, we're gonna give it our command pool here. Probably a reference though, or isn't it? Wait, what the heck? What's going on here? Oh, that's supposed to be. Wait, let's actually unwrap that result. Other than that, let's see what else we have. So command buffer count. We're just gonna go with one command buffer. I'm gonna basically use this command buffer just for transfer operations later on. And yeah. Other than that, what we're gonna need else? So I think right now we could just maybe create this surface and so on. And also we need command, well, let's do this and this. Is that good enough? Right, good. Now we need a render, I believe. Yo, hello Anki Chubi, thank you so much. Welcome to the live stream. Multiple fields are never read. Okay, so right now this is our GPU, and we're gonna have another struct for our actual renderer, which is gonna go for every single. So like you're gonna have usually one GPU per application, but like you could have multiple renders, like one render per window basically, and so on. Other than that, we're fine. So the GPU, how are we gonna do this? Well, it should definitely take. So we could either go with an arc. Let's see. Should we go with reference counting or what? I mean, maybe. We'll see about that. Let's start with that. So import GPU arc. And by the way, we need to implement drop for GPU before we forget. So implement drop for GPU, fn drop, and we're gonna destroy this stuff. So like self dot device destroy command pool. So self dot command pool. Is this in safe? Yep, it is in safe. So let's wrap all this stuff in save block. And what's up? Yeah, the allocation callbacks. None. Destroy device. And what else? Destroy, I guess, the instance. And that's basically it. Or maybe we should actually use entry instead, or isn't it? Destroy? No, it's good. Alright, so that's basically it for that one. Now the renderer, let's see what we're gonna do here. Well, we're gonna need a surface, of course. So vacate surface KHR, we're gonna need a swap chain. And I think that's... And yeah, I just remembered we probably need to also like load the extensions we need. So like surface extension, I believe, isn't it? I think so, if I remember. Surface instance, I believe that's basically it, yeah. And then you basically load it up. So how are we gonna do that? Well, good question. So after we create our instance, we could load our instance extensions. So surface extension is equal to, though honestly I don't remember how do you load the extensions in Ash. Let me see. So where is Ash? How do you load the extensions? I mean, we could just check out, honestly, or how about we just check out that, wait, this, I guess. Oh yeah, you just give it the entry in the instance apparently. Okay, cool. So let's go ahead and say Ash KHR surface. I recently started learning low level 2. Could you recommend some books or resources? Unfortunately not. It really depends on what you want. Is there anything in particular? Though I don't know much of, books to recommend really. I read a few books, but usually I don't even complete them. But yeah. Like the best way to learn is to just, create projects pretty much and read documentation and maybe watch some talks and stuff, or read some blogs about some particular thing you're interested in, watch some tutorials, and that's pretty much it. Yeah, it depends on what you want. Let's see what we need. So new, we give it the reference to an entry, and then a reference to probably an instance, right? Is that the case? Yep, pretty much. And here we could just pass it up, add the missing field. Now we got the surface extension. Perfect. So now how do we do this? Swap chain, save this to dictionary, and yeah, let's right now implement render. So fnu anyhow result render, or self actually, and let's go to, let's see. So here I think we're gonna take an arc GPU. And how are we gonna do this? Well, for now we're just gonna say to do so it doesn't error for us for now. And I'm probably gonna need unsafe, but I'm not sure, we'll see. Otherwise, let's see what we're gonna do here. So first of all, we need to create a surface. But to create a surface, we need a window. Though, let's see. Window, or isn't it? What is it called? It's like basically we want to create a surface, yeah? And so for that, you need an entry. You need a display handle and a window handle and allocation callbacks. Interesting. So honestly, let's make a function here in the GPU itself for creating a surface. So fn create surface, really, and let's see how it goes. So I guess this would give us back vacate surface KHR, I believe. So let's see. So surface, or create surface, yeah. Create surface, here we need to give it the entry. And the instance, well, of course we need a reference to self here. And oh, you actually have to basically say self dot entry and self dot instance. We're not in C++, okay. And what else? Bruh, come on. Tell me. Oh, we don't need return here either. And this should be wrapped in a save block. Pretty much, and yeah. So it takes 5 arguments, okay, parameters. So entry, instance, and display handle. So here, display handle, huh? I don't think we should, honestly. Should we like save this? Good question. Can we even do that? I mean, let's see. Like if you say display handle raw, I mean, let's try. I'm not sure if it's a good idea. I feel like it's not really a good idea, really. So let's just take it as an argument again. Yeah, let's just do that. In fact, we're gonna need the window anyways, and in a second. So let's grab the display handle, and what's next? And next we're gonna need, there we go, the raw window handle. So the window handle. I believe from the window handle you could probably grab the display handle, though I could be wrong. Window handle, and what's next? Display handle, window handle, allocation callbacks, which is gonna be none, and well, this is gonna be like an anyhow result of vacant surface KHR. Here we go. Now expected anyhow results. Well, of course, because this should be like okay. Alright, that's good. So create surface, you take display handle, window handle. Though, can't I just like pass in window handle here too though? Can't I? No? Apparently doesn't seem like it for some reason. Interesting. Alright. And that's basically it, I think. That's cool. Now let's come here and say surface is equal to GPU dot create surface. So here we gotta give it the display handle and the window handle. Honestly, you know what? Let's just store that. Fine. I can't make my mind. If there's any problem, then we're gonna fix it, pretty much. Other than that, here right now in create surface, we don't need this. We could just take it from self. And now here in where? Here, I guess. Yeah. So let's just say to do right now. And GPU creates surface, and here we just need the window handle. So this is like your raw window handle, I think. And there we go. Though, yeah, pretty much. Why can't save this stuff? What the heck? Something's weird. Huh. Isn't this like, Well, I need to add a comma there, that's why. And yeah, that's pretty much it, I guess. Fine, never mind. And now what? So we created the surface. Next up, we should probably take the capabilities of the surface. Is equal to surface dot capability. Well, GPU get Well, honestly, for that, we're just gonna make another function here for creating the swap chain, really. So fn create swap chain for a particular surface. And it's gonna be like vk service kchar, I think. And this again would give us anyhow result vk swap chain kchar. And this would be, well, surface. Now let's see how we're gonna do this. So first of all, we're gonna need the surface capabilities though, which is basically, no, we need to grab the instance, I guess. Actually the surface extension, yeah. Get surface capabilities. And here we give it the physical device and the surface we're interested in. And of course this is in safe, so let's wrap that. Now that we got the surface capabilities, should make sure to unwrap that result. Next up, we could actually create a swap chain. So let's see how we're gonna do that. Well, we actually need to load another extension now, which is the swap chain extension. So like the surface extension is like just the instance extension. The other one is for the device. So hash kchar swap chain device. Now for the swap chain extension, what we're gonna do, so after creating the device, I'm gonna come here and say swap chain extension is equal to hash kchar swap chain device new. So here I'm basically loading the function pointers of that specific extension I'm interested in, because like the regular device and instance objects just like loads the core Vulkan functions of that particular version, and that's basically it. So yeah, now we just need to store that in, and now we're good. So let's actually use that now. Swap chain is equal to swap chain extension dot create swap chain, and here we need swap chain create swap chain create info kchar default dot surface, and we can just pass it the surface that we're interested in. And there's some other few things too, like the old swap chain, which we're not going to care about for now. It's great you are describing everything as you go. I'm also learning a lot. Yeah, I'm trying to. You're welcome, mucho. Alright, so clip true. If you guys have any question, please let me know, because I have done like this Vulkan initialization crap like 7,000 times. Because like I keep switching between languages and so on. But yeah. So, let's see. Provide the argument, sure. So this one, just none. And clipped don't really matter. It's just like an optimization thing, right? So basically we want to create a swap chain for this particular surface, and there's some other, of course, some other stuff that we're gonna set here. Clipped is only useful like if you're gonna, let's say, take a capture of the swap chain. Then if the window is like hidden behind another window, you still want those pixels to be valid. In that case, you can't set clip to true. You should set it to false, so you can get valid pixels even if the window is hidden by another window. But in our case, we don't really care about that, so we just set clip to true for best performance. So those pixels, we just basically say we don't care about the pixels that are hidden. That are, hidden by another window. And that's the clipped. Next up is, let's see, image array layers. We're gonna go with just one. This is useful for stereo rendering. For example, let's say, you know, you're making VR kind of application renderer thing like that. Then you gotta have like 2 of these essentially, and so on. I've done Vulkan, C++, and then Rust. Now I'm rewriting my Rust engine, so this is the perfect stream to get into. Yeah, that's pretty much it. Alright, so composite alpha. VK composite alpha KHR. Honestly, I'm gonna keep that. I don't care about that one. We could keep it as default. Next up, image extent. Okay, well, we need these. For now, we're just gonna hard code the format. Really, we don't care. We're gonna hard code it to sRGB, RGBA 8 sRG. A lot of these things, like you would for production grade, I guess you would like check if the user have these and so on. But to be honest with you, even if that's the case, like, you know, just keep, like, if the user doesn't support, like, for example, that image format, the create swap chain function would fail anyway, so why check it? Like, if you don't have a fallback. But the check-in though would be useful to provide a fallback. But if you're just gonna check and just, like, you know, tell the user it's not there, you know, the create swap chain would do that for you, really. Either way, what else? Image array layers, image extent, that's also something we need, and image usage. So let's start by the image extent. We're gonna need the image extent. Okay. For that, the extent of the swap chain. And that would basically, we're gonna get it from WinIt, basically the size of the window. And next up is the minimum image count. For this one, I'm just gonna hard code it. Like, I mean, there's just basically, you just set this to minimum image count +1 and don't really think twice about it. It's just like how much images you want your swap chain to have. Like, is it double buffered or triple buffered or what exactly? This is kind of like a good heuristic. Everyone just uses that. Other than that, what else? We have clipped, image color space. The other ones, I'm just going to keep them as the default. The image usage, though, is useful. Not useful, I mean, we need to actually pass it up. So image usage flags, we want to tell Vulkan how we want to use these swap chain images. Well, you would usually use them as color image attachments, but I'm gonna start by just clearing the window. And so instead of using like rendering commands, which are gonna need shaders and so on, I'm just gonna start by transfer DST, by a transfer command that too simply just clears the window. So we're just gonna go with transfer DST for now. Later on, we're gonna switch this to color for the shaders and so on, for actual rendering. But we could start there, that's good. Other than that, you could also maybe have an old swap chain. If you would, honestly, let's not bother with that, fine. And that's pretty much it now. I guess we just return our swap chain here. But of course, okay, we're gonna say that we're okay, good. Everything have gone well. Here's your swap chain. That we don't need returning the Rust, since it's the final statement there. And that's basically it for creating a swap chain, I believe. I mean, there's other crap, like you could, you know, for example, let's say control the vsync here and so on, like using present mode by setting the present mode here and so on. But we're not, basically I'm omitting a lot of fields that aren't really required. Like the default ones are fine for now. So yeah, so I don't overwhelm you with a whole bunch of stuff. Other than that, what else we have here? Remove the semicolon. Oh yeah, remove the semicolon so we can return the value. Other than that, we're good. Now we have this create swap chain function. Great, let's use it here. So swap chain is equal to basically. Now the nice way about this is that the user don't even, like, of our engine, because I'm gonna package this as a library later on. But basically, the user don't even need to actually use our renderer class. They could just use the GPU only if they want to. and they create their own custom render if for whatever reason. And they could just use the same functions that we're using here. So GPU create swap chain, and also the other thing why I did this, so I don't have to give access for any other objects of the internal of the GPU, right? So the GPU, like we have this factory functions that takes care of that stuff. And so also I don't have to like, you know, pass a bazillion parameters to every single object just so I can create it. So instead of doing that, I just, you know, delegate the responsibility of creating stuff to the actual GPU, which have access to all those properties and so on. So that's great. Create swap chain. Here we need the surface that we just created, and then we need an extent. And this one, of course, we don't know in this case. We're gonna take it from the user. And of course, let's unwrap this result. And here we need an extent 2D. And well, of course, we're just gonna call extent really. And that's basically it. Now we have our surface and our swap chain. Perfect. Now what we're gonna do? Good question. Let's create the renderer here. Option, render. And here what we're gonna say is self.render is equal to some render new, and this takes GPU, but of course this takes an arc GPU. Though, do we actually need that? Wait, yes we do. So it's basically a reference counted thing. And yeah, let's actually change this to an arc and basically make this into an arc new. And so here I could just copy the arc and give it one. So we use an arc to basically share ownership. So like instead of passing references everywhere, which would make it a hell for us in Rust, since because of lifetimes and so on. Render pass and pipeline soon, right? I'm not, the good news is I'm not gonna bother with render passes and frame buffers because I'm gonna be using dynamic rendering. So I'm just gonna straight up, and also in fact I'm not even gonna need pipelines right now, since I'm just gonna clear the window first. So I can give you something to look at into the screen first. Then we could worry about creating the pipeline and shaders and so on. So yeah. But like, yeah, the regular tutorial would do that, but we're using some modern Vulkan extensions, which would make our job way easier. So I'm going to be using dynamic rendering, which, as I said, would we wouldn't need the frame buffers, and we wouldn't need the as I said, the frame buffers, and we wouldn't need what else? The render pass too. So like basically the ones that don't use it, they have to juggle all these crazy objects that are really unnecessary for modern hardware and just add extra overhead, right? But if you use this modern extension, you don't really have to do that. You just like render directly. You just tell the GPU what the heck to do, instead of like, you know, what is it called? Bike shedding? Yeah, bike shedding the render pass. But yeah, either way, pray to the render pass. Either way. So let's see what we got here. Render pass new. How are we gonna do this? So self.gpu, right? So, and we're just gonna say unwrap here, and what else? The window handle. Well, we did get the window here. And the extent 2D. So extent 2D default, I guess. And what's going on here? Cannot move. Oh yeah, we need to clone this arc. And of course, we're not going to be cloning the whole GPU. We're just cloning the arc, which is the reference count. And when you clone an arc, you just, you know, bump the reference count by 1, and you know, the renderer would get access to it, and it would make sure that as long as the renderer is alive, the GPU would also stay alive, because it have like, it's like, you know, you have a house, like a home, right, which is the inside of an arc, right? And basically this arc would allow you to clone the key, right, and give a key for each one in the house, right? So if there's anyone, like if there's no keys left, then we're just gonna destroy the house. No one is living in it. Right? If there's still some keys left, we're gonna make sure that the house stays alive. Right? That's basically how an arc is. Though there's an RC and there's an arc. There's an RC and there's an arc. RC is actually more performant, but it doesn't care about threads. So if you ever need to meddle with threads, you have to basically use arc. And honestly, for here, I just used arc directly instead of bothering with that. In other words, key house. Yeah, exactly. All right, so let's see what we gotta do here. Self.window. I think .raw window handle. Yep. .inwrap. Use has window handle instead. But like, what the heck has window handle, huh? Like has window handle. Is that the case? For now, let's just use the deprecated one, really. I'm not sure how that works. So the raw window handle .inwrap. And now what's going on here? I mean, I guess that maybe works. Oh, we cannot move window. Oh yeah, since this is an option, if you try to inwrap it, it would just think you want to move the object, you want to take ownership of it, and in this case we don't want to, so we can say as ref to, instead of getting option window, which means that we're gonna own the window, we just use this as ref so we can get an option of a reference to a window, and this would work perfect. Now that's pretty sick. Cool. Now here we actually need to set the width and the height. So the width and the height, well, we do have the window, and honestly I'm getting tired of this inwraps everywhere. So what we could do is, if let's window is equal to self, or honestly instead of that, what we could do instead, we could just create the window straight up here, right, and remove this stuff. Same thing with the GPU. Create the window, the GPU first, and then once you're done with all that stuff, we could set self dot window is equal to sum window. Self.gpu is equal to sum GPU. Now, of course, this wouldn't work if you do it beforehand, because Rust would actually enforce that, I believe, right? Because of course they should be moved, and you shouldn't access. Oh yeah, since here we're using self. Oh yeah, like if you use GPU and window, it's not gonna allow you because it's moved. You know, it's moved to here. So make sure to do it at the end, after you're done with the objects. Ryan McGowan, hello, welcome to live stream. I'm going to watch this entirety later. I want to build a parametric CAD engine in Rust. Maybe take it open source at some point. That's pretty ambitious. Good luck with that. Sure. All right, so that's pretty sick. We don't need inwraps anymore right now. We could just do that. And yeah, that's pretty much it. All right, so we got window, we got GPU, and yeah, I believe now let's try to run this. And we have a crash, or what was that? Not yet. Oh yeah, I forgot to actually return a renderer here. Okay, let's return self. And whoops, let's wait. Oh yeah, we need to return OK self. Add the missing fields, and there we go. All right, perfect. Now, if you really want to see the raw calls that is going to the, to Vulkan, what you could do is open up your terminal if you're on Arch Linux, and make sure to install, what is it called? Vulkan-Devel. Devel stands for development, right? And then you're gonna have validation layers and so on. If you're on Windows or Mac OS and so on, you're gonna basically install the Vulkan SDK from their website. Otherwise, once you do that, you're gonna have a tool called vkconfig GUI. In Windows, I think you're gonna maybe have access to it just in your menu, or you could probably go to the C drive and you're gonna find the Vulkan SDK folder there and check it out. But in my case, I could just run vkconfig-GUI here, and I'm gonna get this thing right here. Now, other tutorials, what they would usually do, they would basically make toggle these layers programmatically, right? Which kind of suck, because like you're mixing up the debugging stuff with this crap and so on. Like these layers actually does take a performance hit, and I mean they do disable it in debug. They use like fdiff and so on, basically conditional compilation. But why bother with all that crap when you have this such an amazing tool which you could easily like do all sorts of cool stuff with it. So here I could choose whichever layer I want to use. So for example, API dump, so I could see what kind of Vulkan functions are actually like raw ones that are being ran into the driver. So I could just do this and make sure this is in any running Vulkan executable. Now I could run my thing, and as you can see right now, it's gonna dump all the Vulkan functions that are being ran. There we go. So this is all the raw C Vulkan functions that are going to the driver, the Vulkan driver, as you can see. And you could inspect it, and you can see that the return code, all of them are vk success, vk success, vk success, and so on. There is another thing, which is the validation layer. Yep, that's very awesome, and I'm not sure why tutorials don't like cover it. They usually go through a whole bunch. Also, another note is that in other tutorials, another thing they would do is, for example, the physical device. They would go through a whole bunch of crap to programmatically make sure that the physical device is compatible and so on. I mean, you would want to do that in a production engine, but since you're just starting out, you really shouldn't really care about all those stuff. Just take the first physical device you can find, which I'm doing here. So this enumerate physical devices just gives you all the GPUs that are in this system. And here I'm just, taking it into an iter, which basically consumes the vector here, because I don't need it anymore after this. And I'm just taking the first element of that vector and enwrapping it, because it's an option, because you could maybe find no functions there. And that's basically it. Honestly, instead of unwrapping, since we have here, yes, one tutorial made a whole score system for choosing the right physical device. Yeah, exactly. And I mean, you may want to do that, but like, bruh, for a tutorial, come on. Like, you should just go straight to the point. Another thing is they go straight into a triangle, which is a whole bunch of crap. Right now, what I'm gonna try to do for you guys is to just show you how to clear a window without shaders, without anything, just using Vulkan commands, raw Vulkan commands. And that's basically how it goes. Alright, so where I was. Alright, so another layer here is called validation layer. And basically, all these layers actually goes in the middle between the driver, the Vulkan driver, and your application. They basically check your they can intercept. They're like the middleman of your function calls to the Vulkan driver, right? And they could do all sorts of stuff. They could, for example, the API dump just basically just prints all that for you. They print the thread, the frame, etc., and so on. The other one is validation. This one makes sure that your usage of the API, it checks your arguments and the success code and so on. and make sure you're using the API right. Otherwise, it tells you that you're not doing this and not doing that, etc., which is pretty good. So make sure whenever you're creating, developing your application, that the validation layer is on. If you want to disable this so you have the best performance, then just set this to no Vulkan executable, or just basically quit this application. Once you quit it, it's gone. And that's pretty much it. Alright, so let's try this validation layer, making sure we're not missing any parameters. Okay, we are missing some parameters apparently. As you can see, the validation layer will tell me. So for example, here it's telling me that the pre-transform parameter. So in vk create swap chain khr, p create transform pre-transform is 0. The Vulkan spec states pre-transform must be a valid vk surface transform flag bits khr. Same thing with composite alpha, same thing with the image extent. Apparently it's invalid 0, 0 for some reason. Alright, so let's actually fix those. Let's go to where we're creating the swap chain here. And let's see what's going on. So first of all, we got the extent. Where we're taking the extent? We're taking it from here. And here, as you can see, we're saying default. Well, let's actually set the width and set the height. But of course, we're going to take that basically from the window. So let size, like window size is equal to window dot size, I believe. Inner size. So like the outer size is like including the title bar. The inner size is like the place where we're actually going to render to. So we're going to take the inner size here, and we're just going to say window size dot width and height, window size dot height, pretty much. And that's basically for it for the extent. The other thing is we have to add some few things, as we've seen in the validation layer. I have forgot like the pre-transform here. So I should set it to something, and in this case I don't bother. I'm just gonna set it to current transform. You really shouldn't care about this stuff. It's just kind of like boilerplate for now. When you're more advanced, you may want to care about these, but for now I just set them as you see here. Here this is basically about if you want to make your window transparent and you want to do some transparent rendering, then you may want to mess with this, but for now we're just going to keep it opaque pretty much. And that's basically it. I believe that's all for now. Let's check out if we have any other validation problems. No, we don't have any anymore. So that's good, which means we are using the API right. Cool. Next up, what we got? So we created the swap chain, we created this. Now we need the synchronization stuff. Now this is a very hard topic though. I think I'll see how I'm gonna handle this. Alright, let's see. So, of course, this would, I believe, go in the renderer. Okay. So, honestly, every renderer would have its own command pool and command buffers. So, like, the command pool is what we use to basically allocate command buffers. And the command pool is not thread safe. So, every thread you use, because, like, Vulkan actually allows you, like... It's not like OpenGL. I mean, even in OpenGL, it could do multi-threaded rendering, but it's so icky and it doesn't work always. There's a whole bunch of problems, even single-threaded, right? But Vulkan, no. Vulkan, it's like designed from scratch for multi-threaded stuff, like to basically exploit all your CPUs. GPU performance, it's honestly... not that, I mean, it depends if you're using modern extensions or not. I mean, in fact, you could make a Vulkan application that is way slower than OpenGL, because like the thing is about OpenGL is that like most of the code is in the driver. It's done for you, right? But here in Vulkan, like you write a lot of the code, like most of the code, the driver is very thin. There's not much going on in the driver. And so here, since you know your application and what kind of stuff you're gonna do, you can optimize it better than the driver. In OpenGL, the driver basically kind of just guesses what you're gonna do. And if it gets correct, then great, we're good. If it doesn't guess correct, then you get that stutter because it's gonna basically flush and restart again, try to guess again. And you see how that goes. And also it's not multi-threaded. Either way, the point is that this command pool is not thread safe, which means that every thread should have its own command pool. And here I have a command pool, command buffers, but I'm gonna use it for other stuff, for the kind of like the global GPU stuff, like for example transferring, let's say, the texture into VRAM, into the GPU memory, and so on. But every renderer I would like to have its own kind of command pool, so I could basically run this renderer in its own thread, for example, with no problems. I mean, of course, there's some other stuff that I have to take care of, but this is a good start, right? So command pool, command buffers, there we go. And let's go. The other thing I'm gonna also need is fences and semaphores. So semaphores, vacay, semaphores, and fences. Oh my god, like, you know, programming in Rust instead of C++, a lot less cognitive load. Because the syntax is so clean, like, oh my god. Anyways. Let's see. So add missing fields. So in C++, like, this kind of initializer list goes here. Why, I have no clue, but it goes here. And you just have to stuff that in. And in Rust, it goes here, the last, basically. Almost 3 AM, thanks for the stream. Goodbye, Burius. See ya maybe tomorrow, or I don't know. I'm gonna look for something to, like, some water real quick. Okay, back. Just got hydrated a bit. Oh my god. Alright. Let's see what we got here. So we gotta create a command pool. Now to create a command pool, we're gonna need a function, of course. So here, fn create command pool. Now for creating a command pool, we're gonna of course take self again. And basically here, I guess we're just gonna, the only thing that is needed for a command pool is basically the, what is it called? Did I, by the way, enable the mic? Good. All right. Which is the Q family. Now, I didn't really spoke about Q families a lot. Now, a lot of tutorials would actually, you know, set up Q families and stuff. But here, you know, just assume that it's 0. And to be honest with you, just so I don't overwhelm you, I'm just going to assume it's 0 and not even make it a parameter right now. So, yeah, just to keep things very light. So, create command pool, it would return anyhow result of what? Of vacay command pool, right? Now here what we're gonna return OK and self.device.create command pool. Here reference of vacay command pool create info default dot Q family index. Here is the Q family index. Right now I'm just gonna assume it is 0, honestly. The other thing though I need is the flags. So flags are interesting. For now, I'm just gonna hard code it as reset command buffer, so we could reset individual command buffers in those that are allocated from this command pool. This is the first thing, and the second thing, we're gonna set this to, for now at least, transient, which means that these command buffers wouldn't stay for too long. They're just, you know, record and start again and so on, I believe. But yeah, this is kind of like just hints to the driver to optimize some stuff, but other than that, it's fine. Now let's just say in safe, because, you know, like allocations that are temporary aren't like the allocations that are not temporary. It's gonna stay for too long. You know, they have some different lifetime, which would better be like allocated in another kind of place in some sense to avoid fragmentation. But yeah, that's kind of just something to keep in mind, I guess. It's not really important right now. Either way. Now that's good. So this would create a command pool. And next up, we want to allocate command buffers. And for this, you're going to give me a command pool. Yeah. Is that right? Actually, without the reference, because these are just like handles. And then what? Result, well, actually vector of vk command buffers. Of course, we're gonna need the result though. There you go. So here we're basically gonna say in safe. Okay. Hello anonymous, welcome to the live stream. Self.device.allocate command buffers. vk command buffer allocate info. There we go. Default. Oh wait, what the heck? Oh. Command buffer allocate info default dot command buffer count, and this is where the command buffer count goes. So this we're gonna take it from the user though. Well, here we go. U32, I think. Yeah. And there we go. Perfect. Perfect. And we also need to make sure to put the command pool 2. And there we go. Now we could use these functions. Let's go. So first of all, our own command pool for this particular renderer is GPU create command pool. Now, even in every renderer, you may have multiple command pools. One, let's say, for example, for graphics, and one for uploading resources, for uploading textures, for example, to VRAM, to the GPU memory. And here, for now, we're keeping things very simple. And allocate command buffers, we're gonna give it our command pool and how much buffers we want. Now we're gonna have something called in-flight frames, and for now I'm just gonna hard code it as 2. Now let me try to explain in-flight frames really quickly. Let's see. So basically, while the GPU is working on one frame, the CPU could, instead of just waiting for the GPU to finish, like working on that frame, what we could do, we could prepare a new frame for the GPU while the GPU is busy. That's what in-flight frames is for, right? But of course that needs some extra synchronization, which is not very trivial, especially for beginners. And you could in fact prepare either one frame ahead of the GPU, or 2 or 3 or 4. So this is what we call triple buffering or double buffering and so on. Now the more you prepare frames beforehand, before the GPU, the more FPS you could have. But there is a catch though, which is the more latency you're gonna have. Right? Why? Because, well, let's say you're preparing, like the CPU would prepare the frame at tick 1, right? And so it would also prepare, well, let's just say, so basically the GPU, instead of rendering one frame that is just, 1 second, well, that's too much. But like 1 tick behind, it would be rendering some frame in the past, like 2 ticks behind and so on, depending on how much you have there. Either way, right now we're just gonna go with double buffering, which is kind of like a good middle ground between latency and FPS. If you really doesn't care too much about latency, but you care much about the FPS, then you're gonna go with 3 here, triple buffering. If you care more about the latency, then you may want to just go with 1, which is kind of like immediate mode, right? So the CPU prepare it, the GPU render it, and that's pretty much it. But either way, right now what we're gonna do, so we're preparing that, cool. And next up, we need the fences and the semaphores. So we basically, for every single in-flight frame, we need also semaphores and fences. Semaphores are actually used to basically synchronize. Now the thing is, let's say, for example, there is a function in Vulkan called submit command buffer. Now this submit command buffer, essentially what it does is it tells the GPU to run some commands. Now of course those commands would take time to do, like for example drawing into the screen or so on. But the thing is, when you call this function, it returns immediately. You're not waiting for the GPU to finish like OpenGL. No, like the application, once it's done, the driver gives you back control, and then you could do some other stuff while the GPU is working on those commands. Now, sometimes you do want to synchronize, right? Let's say you want actually the CPU to wait for the GPU to finish. Then you want to do something for whichever reason. Then what you use there is fences, right? So fences basically helps you to synchronize between the CPU and the GPU. For example, to make the CPU wait for the GPU to finish rendering. Then you do something, for example. Semaphores, on the other hand, you synchronize between the GPU queues, between the GPU stuff. So like, let's say you run some commands in the GPU, all those commands would basically run in parallel. Like, for example, let's say you have rendering and you have compute. You're doing both, right? Those two would run at the same time in the GPU. Now, if you don't want that for whichever reason, like if you want to synchronize between them, like let's say you want the compute to run after rendering in the GPU, then you gotta use a semaphore. Hello Arnold, welcome to the live stream. Make my brain hurt. Yeah, this is some very advanced stuff, pretty much. Very advanced like graphics API stuff, but yeah. Alright, so that's pretty much it. Now let's actually make some semaphores and fences. So how do you do for loops in Rust again? Good question. Oh yeah, I just remembered. Let's see. So you say 0 to 2 and for I. Right. Or I just remembered my iterator stuff. We could say semaphores is equal to 0, 2 dot map. And here's your index. We don't need the index here, and we're just gonna say gpu.create. Well, I haven't prepared that function yet, so let's make a create semaphore function and let's go. So fn create semaphore. Return self.device.create semaphore. Now what we're gonna do, well, actually need to take a reference. Default dot what's here. I don't need any flags. I don't need to return. Do I need to say okay? And this is an unsafe operation though, so I'm gonna basically need to say this. And what's up? Oh yeah, let's actually unwrap that. Well, you missed something important from 1.4 since Ash is not up to date. Not really. So I would miss the fact that push descriptors, which I'm going to use instead of descriptor sets, which really sucks. I'm going to use an extension called push descriptors. But the real difference between using it in Vulkan 1.4 and Vulkan 1.3 is only the fact that in Vulkan 1.3 you have to enable that extension. But in Vulkan 1.4 it got promoted to core, which means I don't have to enable it because it's already in the Vulkan core API, right? It's already there as long as you're using Vulkan 1.4. And since we're only going to be using Vulkan 1.3, we have to enable it explicitly and make sure that the user does have it. But yeah, so I wouldn't really miss anything. I could just enable the extensions I need. Mostly, at least. Either way. So this takes 2 arguments, I think. Cool. And that's pretty much it. Now that's create semaphore. We're gonna need another one for create fence. Create fence. Now this one I'm gonna start it as signaled. So fence create info. Wait. Flags. Vacay fence create flags. E signal. Well, signaled. Never heard of that. Sounds like push constants plus descriptor set. So basically with the regular Vulkan, you have to create a descriptor set layout, a descriptor set, a descriptor pool, and all sorts of crap, right? So a lot of objects you have to juggle, and every time you need to add a new uniform, you have to like change 4 places and so on. And it's really very confusing. But with push descriptors, what we do, we only have a descriptor set layout. We just tell the GPU what kind of descriptors we're going to have, and we just push them directly into the GPU, like in the frame, where it's like draw, like literally. So basically, it's like dynamic render, where we don't need extra objects like render pass and all that crap. Now here, push descriptors, we remove some other objects that are very annoying too. That's basically how it's more like ergonomic and a bit more performance too in some devices. But yeah, could be slower in some other devices, but usually that's very old hardware that I personally, at least, I don't care about. Either way, what else? So create fence. See signaled, especially if you're a beginner, don't really care about other machines, just care like, does it work on your machine? If it does, fine, good. Because like compatibility and cross-platform really, there's too much effort that goes into it. Like for example, Android, there's a whole bunch of crap that you have to care about with Android. And I mean, this stuff that I'm making right now would probably work with Android too, but well, I mean, Android doesn't support really Vulkan 1.3 though. I think it only supports up to maybe Vulkan 1.2 and some older device even just 1.0. But either way, whatever. But like when the devices get better, it would be supported. So anyways, so what we gonna do now? This is some stuff I wish I knew sooner. Create semaphore, create fence. And what else? So now we got that. Now let's actually create some semaphores here. So create semaphore, and we're gonna collect it into a vector. Same thing with defenses. And that's basically it, I believe. Now, can we just add the missing fields? Well, I see what's happening there. We need to make sure to tell it what to collect it into. And we basically want to collect it into a vector. How are we going to do that? I believe like this. No? Huh. Oh, I could do this. I'm just remembering my Rust stuff. Oh my god, so much better. Oh boy. I was trying so bad to shoehorn like C++ ranges like this. Oh my, look at that. Just one line, pretty cool. Anyways, add the missing fields. Well, I forgot to, I see. So how are we gonna do that? Well, this is basically like a vector of results. What we could do, I remember there was some trick to like, let me try to remember it though. I believe maybe if you do it this way, is that the case? And I guess you could, yeah. Great, I haven't forgot like the Rust tricks, huh? So basically we had like a vector of results, but we could turn that into a result of vector. And then you could like propagate that result. So freaking good. I love Rust, man. I really love Rust. Yeah, when I knew this, like, when I realized this like years ago, that was, oh my god. Same thing with this guy. And there we go. Look at that beauty. I really love functional programming. And the nice thing about this collect right now, since it would basically detect that this kind of range, this iterator would have two elements, and so it would make sure that this vector, you know, it would reserve upfront two elements. I don't have to tell it to reserve, for example. And I could, of course, as you can see here, it basically compose seamlessly too. So that's cool. And yeah. If you weren't using this iterators, then you would have to basically create a vec, you know, let's say a vec new kind of, and then you would have to reserve, or otherwise if you don't, then it would basically reallocate every time you push a new element and it doesn't have enough space and so on. But here using iterators, it's all automatic essentially, right? But yeah, that's basically it. Now let's add the missing fields. And let's see, let's actually do this, and there we go. And yeah, there we go. We created the semaphores, we created the fences, the command buffers. For the swap chain, we're also gonna need its swap chain images though. So let's grab that. So vk image. There we go. Well, actually, this should be a vector. Oh my god, I love Rust. Chain, as long as I'm not fighting the borrow checker. Alright, so swap chain, swap chain images. And also the Rust analyzer is so much more useful. Oh my god, productivity is wild. So swap chain dot, well actually self.device, or isn't it? No, I can't. Oh yeah, well, okay, so we gotta need another function here then. So fn get swap chain images apparently. Swap chain vk swap chain khr. Well, this would basically return a well, what is it? Anyhow result. Yep, vector vk image, then we're gonna return. Well, I probably need the unsafe crap again. Well, this is another thing that I kind of hate. Well, I also like about Rust, but either way. Okay, and self.device dot, well, what is that called? Get swap chain images, I believe. No, actually we need to use our swap chain extension. No, get swap chain images pretty much. Give it the swap chain and there we go. Perfect. Lovely. And that's basically it, I believe. Yep. Now let's use that here. Swap chain images is equal to swap, well, GPU dot get swap chain images, swap chain. And let's propagate the error to the caller. And right now I could just say show context, add missing fields. There we go. And we got that out of the way. Now, do we need anything else? We got surface, swap chain images, command pull, command buffer, semaphore, sense. I believe that's probably it. Yeah, I think so. So right now we need a render function. We're finally done with the preparation. So here, run. Well, actually not run, render. Okay. So let's see what we're gonna do here. Well, we're also gonna need to keep track of which in-flight frame we are currently in. So we're gonna keep track of frame index. U32, I guess. And here we're gonna say, well, actually, right now we need to basically, first of all, wait for the fences. Yeah. So how are we gonna do that? Well, let's make sure to add, by the way, this guy right here, pretty much. Well, you GLSL or WGSL? For now, GLSL. For now. But honestly, in fact, we're not gonna even touch about shaders right now. Right now, we're just purely just focused on clearing the window without shaders, without anything, just Vulkan commands. We're just gonna tell the GPU to clear the image. That's using the transfer command, not even a rendering command. Then after we're done with that, we're gonna go to the next step. So yeah. All right, so okay, we need to prepare some functions here in our GPU. Let's see. First of all, we need some way to wait for the fences. So wait for the fences, self, comma, fences. And vacay fence. And let's see what we're gonna do here in save. Self.device.wait for fences. And I believe this returns a result, right? Yep, it does. So fine. I choose WGSL and regret it and won't ever come back. Why? Why? Probably because you didn't find any kind of like learning resource about it, and especially if you're like me, you like to experiment with new extensions and you're only gonna find like samples for GLSL. That's the first thing. Second thing is the compatibility with Vulkan. Which one was it? Want to be a fancy pants with pure Rust. Naga. WGSL has Rust-like syntax, but it wasn't worth it. Like, what kind of... I mean, I had that in mind at some point. Like, what kind of challenges you faced? Just so I know. You really boosted my urge to learn Rust. Yeah, it's so good. Welcome to the live stream, Kino. Alright. Well, how are we gonna do this? I think like this, or wait. Actually, we need to say okay, and basically unwrap that result. And what's up now? What? Let's remove the semicolon there. Replace with U64 max, sure. And yeah, we're gonna wait for all the fences, U64 max, fine. I mean, we could, you know, later on, if we need those parameters, we could in hard code them and put them as parameters. But right now, let's keep things very simple. And that's basically it. So I remember WGSL didn't even support something I wanted could be implemented now. I also didn't like how huge the functions are. This is basically have an input, argument struct, and return a struct. But just lie out, blah, 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 in and lie out, blah, blah, out is much nicer personally. Yeah, I see. I could try it sometime, maybe. Probably not now though, since I want to experiment with a lot of modern Vulkan extensions. And C++ just didn't get out of my way to do it. But hopefully Rust would. But we'll see about that. Either way. So right now we got wait for fences. The next thing we're gonna need is acquire image. Which basically gonna need a swap chain. And like vk swap chain khr. And let's see. I'm not sure what this would return. We'll see. And safe, okay. Self.device.acquire swap chain. Well, what the heck? And Naga crate. Shader compiler has the worst errors. I'm getting flashbacks. What kind of errors? Why? So self.swapchain extension.acquire next image. It doesn't even tell you what's wrong, not even the line to error. I probably were doing something wrong, because like, you know, in WGPU I believe it did. Though I did had some problem with it, but I was just maybe missing some weird callback error thing. I don't remember exactly what happened, really. But yeah. Either way, let's see what this function takes. It takes a swap chain khr, which we have here. And what else? It needs timeout. Right now it's kind of hard to code this to use 64 max. This guy need help. This is some messed up PTSD. Mucho, there's a whole Reddit post with a poll about Naga error messages. It's a disaster. I see. Right, so here we got semaphore and a fence. Semaphore and a fence. I mean, fine. Let's pass them in. Why not? And let's basically say vk semaphore. Oopsie. Semaphore vk fence. And oh. I thought I was programming C++ right now. So, parsing error there. I'm not talking about the language, I'm talking about my brain. Either way. Let's see what we got here. Expected that. Okay, fine. Add expect. Oh, maybe I then... wait. I think I need to return a result, right? Well, actually, what this returns though? Wait. It returns U32 and bool. Alright, fine. So basically, anyhow, result U32 and bool. And there we go. Now, what are we gonna do with this? Add that, and there we go. Perfect. That's the acquire image function. What else? And finally, well, actually not finally. Well, we're gonna need some way more crap. Well, and we're gonna need present image. Well, I mean, I guess maybe we could just copy this over to some degree. Present image. It's a lot of boilerplate code at first, but then after you abstract this stuff, it becomes easier and easier and easier. So error message is like, you can't do Naga expression 35 to Naga expression 17. Yeah, that means nothing. Yeah, there's probably something that you could maybe implement to make it better. I'm not sure, but yeah. Present image. Well, actually, I think that's in the swap chain. Wait, swap chain extension qpresent. Yeah, there we go. Now what this takes? It takes a Q, which we have here, and the present info. Let's see what does present info have. So swap chains, of course, first of all, which we're just gonna give it our swap chain here. Well, it needs a slice. And what else? The image index we want to present, and the weight semaphores. Sure, image index. Image index E32. Though we don't need, I believe, these for now, maybe. Actually, I may need them, but let's see what's going on here first. This needs that. Wait. Expected U32 bool, but found bool. Makes sense. Sure. And I believe fake result. Okay, cool. Now what? There's also some other stuff, of course, which is weight semaphores, which we do actually need. So, well, fine. Weight semaphores. It's basically a slice of decay semaphore. Alright, cool. That's present image, acquire image. We're also gonna need submit commands. Or like submit command buffer, I guess. Right, so let's go ahead and, well, honestly, let's just copy this, paste, change this to submit command buffer, I believe. And here, let's see, let's say, I would literally read my shader top to bottom, character by character to catch the error. Oh my god. Submit command buffer. Let's go. Oh, no, not that. Let's go with, I guess, Q. Wait, what the heck? Wait, bruh. Self.q. Well, actually, no, I see. So self.device submit command buffer. Well, q submit apparently. Okay, cool. So here you give it like the q, which we have here, and then you give it the submit infos. And for now, we're just gonna hard code it to one submit info just to keep things very simple, I guess. So command buffers. Wait, semaphores, signal semaphores. Oh boy. Well, that's a lot of stuff. Defense. Sure. So let's remove this stuff, and we basically need the command buffer and the fence. Now, what this would return, by the way? Nothing. So let's just do this, and that's pretty much it. Now, we're basically gonna set the command buffers here. Command buffer. Or to simply make this command buffers instead. Why not? And what's next? wait semaphores, signal semaphores, and wait DST stage mask. Dark buffers are good for modern Vulkan, right? Well, there is a whole bunch of extensions that could allow you to like basically put everything in buffers. So you could like everything could be used in compute shaders. It could be used everywhere. Like for example, you could use the buffer descriptor extension to basically put the descriptors in a basic GPU buffer. So we could even process them in the GPU using compute. You could put your vertex data into a GPU buffer too, like a regular one, not the vertex buffer that you pass into the pipeline layout. So you don't have to tell Vulkan what kind of format, like you just read it directly from the shader, which is great. Honestly, very cool. It's called vertex polling instead of vertex fetching, which is honestly the same performance in AMD at least, because like AMD basically does the same thing under the hood if you don't use vertex polling yourself. But NVIDIA, on the other hand, they have like dedicated hardware for vertex fetching, so you do kind of take a hit, unless if you offset that by doing some, some clever things like with vertices, like some optimization with that kind of flexibility, right? For example, let's say you're making some voxel game like Minecraft or something. You could like using that way, that buffer, you could like using vertex polling, you could pack all your vertices into one integer or something like that, crazy like that, using that way. But yeah. So here we got wait semaphores and signal semaphores. Okay. So honestly, let's see. Wait semaphores and signal. What the heck? Signal semaphores. All right. Whoa, I had no idea extensions were so cool. Yeah, too much. As long as your target hardware do support them. But like if you only really care about like modern hardware, then yeah, you're good. There was a database that you could actually check out which GPUs actually support which extensions. But beforehand, I actually checked them out lately and they were down for whatever reason. I'm not sure what's up with the internet nowadays. Everything is down. But like GPU database, Vulkan. Yeah, I'm not sure why it's down. So there is this one right here, but for some reason, I'm not sure why it's down, fortunately. But basically, this had a database of GPUs and it tells you exactly like what kind of features, what kind of extensions, what are the limits, etc, etc. And basically you could also contribute yourself to the database by uploading your own GPU data, driver data. And it basically differs from driver to driver and from operating system to operating system and from GPU to GPU, obviously. And that's pretty much it. Now let's actually say wait semaphores. Wait semaphores. Vacay semaphore. Wait, what the heck? Wait semaphores and signal semaphores. There we go. Do we need anything else? I believe maybe that's it. So submit command buffers. Right. Present image, acquire image. We're also gonna need reset fence. We could just copy this and call this reset fences. And instead of wait for fences, we're gonna say reset fences. And we don't need these. That's reset fences. Is there anything else we're gonna need? I believe that's maybe it. Now, let's just use it, I guess. Since now we kind of made a little abstraction over that stuff, now our code would be much cleaner in the render function. So we're gonna say, acquire image. So here we give it our swap chain and our semaphore. which is basically self.semaphores. And our index here, what is it? Frame index, yeah. Self.frame index, comma, fence. Self.fences, self.frame index. And that's basically how it goes. Now what's up? The type semaphore cannot be indexed by U32. Oh, I see. Honestly, I'm gonna make this U size instead. Why not? And there we go. Cool. To do. Now, acquire image would give me the image index and is suboptimal. I'm gonna ignore suboptimal for now, I think. Do I really need these? Yes, I do. Okay. So now we got the image. Well, actually, before we even acquire the image, we're gonna make sure that it's safe to do so by basically waiting for that to finish. So we're gonna say self.gpu.wait for fences. And yeah. Now, after we wait, we basically, if everything have gone well, now later on we gotta actually maybe basically make sure if it is some error, then we could like recreate the swap chain and so on. But right now we don't care. Like if something bad happens, we just crash. So after that, if everything goes well, we're just gonna reset the fences. And then what we're gonna do? We're gonna start recording to the command buffer. Oh boy. Well, that's gonna be interesting. And after that, what we're gonna do is self.gpu. Like basically you gotta submit the command buffers. Command buffers. And so self command buffers image index. What the heck? Self.command wait semaphores. So we're gonna wait on image acquired semaphore. Do we have that yet? Actually, we don't. Well, oh boy, we're gonna need a lot of crap here. Well, okay. Fine. So we're gonna call this image acquired semaphores. And we're gonna basically make another one here called rendered finished semaphores. Is re-recording all commands each frame okay, or is there a better way for updates? I mean, you could pre-record that. Especially here, we have very simple command buffer. Like if nothing changes every frame, which is we do here, but it doesn't really matter. I mean, in fact, if you do anything trivial that any application would do, you would need to re-record it every frame anyways, right? So it's not really much. So yeah. So anyways, so render finished semaphores, image acquired semaphore. By the way, is the Rust femboy theory true? Not for me at least. But I don't know. Image acquired semaphores. Let's go. Render finished semaphores. And we're good. And is that it? I believe so. Reset fences. All right, now let's try to actually submit the command buffers. So honestly, let me grab GitHub Copilot. It may help me here to cut down on a lot of boilerplate, really. The default AI of JetBrains is so basic. All right. Come on. Well, anyways, let's just do it ourselves for now. So command buffers, self.command buffers, and I'm gonna say self.frame index, comma here the wait semaphores, which is basically gonna go with self.wait semaphores. So what we're gonna wait on? We're gonna wait on image acquired semaphore. And we're gonna say self.frame index, comma. And here the signal semaphore. I'm not sure why the wait. And GitHub Copilot didn't want to install for some reason. Fine. Now what's up? Expected, found. Why? Well, that's weird. Either way, what we're gonna need next is the fence. So self.fences, self.frame index, and there we go. Now I'm not sure what's wrong here. Am I missing something here? Oh, I see. I'm missing this. So that's why. I'm missing it here too. Okay. Is that it? Oh, this is signal semaphore. So we're gonna wait on image acquired, and we're gonna signal after we're done. We're gonna signal render finished. And here we just give it the fence, really. And there you go. So what we're doing here, basically, we're gonna submit some command buffer that we're gonna record here in a second. And before we execute those commands, we're gonna wait for the image acquired to happen, which is gonna be signaled by acquire image. So like, basically, first of all, we tell the swap chain to give us an image. And once it's done, it's gonna signal this semaphore called image acquired semaphore. And it's also gonna signal this fence that we're gonna use later. Right, and then we basically reset the fence, and here in submit command buffers, which is the one that's going to do the rendering, we wait on the image acquired semaphore, right? And once we're done, we signal the render finished. And then after the render is finished, we're going to present. So present the image, of course, swap chain, and then here the image index. And the wait semaphores here. So which semaphores we're gonna wait on is the render finished. So we want to present until the render is finished. And that's basically it. Now, as you can see here, this reset fences, acquire image, submit command buffers, present image, all of these wouldn't wait for the operation to finish. They just would return immediately. The only thing that would actually synchronize is these semaphores and stuff like that, right? That's essentially it. Great. Now we actually gotta basically like record the command buffer, and we're gonna cheat here. We're not gonna make like a whole another freaking GPU function for now. We're just gonna cheat real quick. We're gonna say self.command buffers, right? Self.frame index, and then we're gonna basically reset that command buffer. Well, yeah, we have to use self.gpu.device reset command buffer. Command buffer here, we're gonna say command buffer reset flags most of this is just like, you know, the boilerplate, the first of the first stuff, right? But later on, once we have abstractions and so on, it's going to be way easier. But either way, right here, we don't actually need anything really. So I'm just going to keep it as defaults. Yeah, let's go. Now this is of course in save, so let's wrap it in a save block. So we're gonna reset the command buffer, and this could fail, I guess. Yeah. And next step, what we're gonna do, we're gonna begin the command buffer. Command buffer begin info default dot flags vk command pool one time submit. Yep, there we go. Next up is, let's see, honestly I'm gonna store this device real quick here. Wait, self.gpu.device. And so I don't have to like retype it every time. I could just say device, and there we go. Honestly, let's put it inside this block so it's limited to that scope. Fine. And now what we're gonna say is end command buffer, of course. And now between begin and end, what we're gonna do? Well, we're gonna clear the image. So clear cmd clear color image, and we're gonna give it the command buffer that we're recording into near the image. So the image would basically be the swap chain images, and here the image index that we got from the swap chain that we acquired, and here the image layout. It's gonna be basically transfer DSC optimal, which is the best layout for this operation, and clear color value default dot. Since we're using sRGB, we should use float32. This is like a union, either float32 or int32 or uint32, depending on the image format. And here we're just gonna use that, I believe. Well, why that doesn't work? Oh, I need to set it directly. Okay, so I'm just gonna take this. So this is my clear color. Let clear color is equal to this, and then hopefully I could like set the clear color here to is that it? Though I need to make sure that this is mutable, I believe. And oh, I guess maybe I should just say this. Yeah. Alright, cool. And here what's up? How do you cast in Rust? I forgot. Let's see. As, oh yeah. As you size. There we go. And what's up? Ah, yes, image sub-resource range. Oh boy. I'm gonna try to actually explain all these in a second. Level count 1. This is mostly just boilerplate. Hello, mid blur. Welcome to live stream. I think that's good. I believe we maybe need this. Ah, yeah, it should be a slice. I see. Now here we're gonna say dot aspects mask, vk aspects mask. Well, image aspects flags e-color, or color, actually color, yeah. And that's basically it. I mean, let's just don't run the validation layer for now. So we're beginning the command buffer to start recording the command buffer for the GPU. Here we're just setting a clear color, you know, R, G, B, and A, red, green, blue, and alpha. The Rust 00F is 00F32 if you want to be explicit. Ah, I see. Gotcha. And here we got device clear color image. So instead of like, you know, preparing a pipeline which is going to take another 2 hours or so on, right now we're just going to use a very simple GPU command called cmd clear color image. This is not even a graphics command. This is called the transfer command, right? And you basically tell it which image you want to clear, which is our swap chain image here using this image index. So basically when we said acquire image, the swap chain engine, like the presentation engine, would tell us which image index is available for drawing, right, for rendering. And here we actually use it, right? So we fetch the swap chain image in that image index, and we just use it to clear that image, right? Here, transfer this, you don't really have to care too much about image layouts, honestly. Basically, some operations require, like, they better work with some exact image layouts, right? I mean, you could just say general for everything, but it's not the most optimized, right? For this particular one, this is a transfer operation, transfer destination, because we're going to copy something to this image, which is basically we're going to copy a clear color to this image. That's why we need to make sure that this is transfer DST optimal. Here we give it the clear color we want to use, and here the image sub-resource range. So the thing is, let's say for example you want to work with 3D images. Like what? Like volumetric, let's say clouds, or let's say MRI scans, right? These are basically, they're 3D images, which means that it's just like a stack or like layers of 2D images, right? Now here you could tell it which layer you're talking about, right? Right now here we just have a swap chain image, which is just a 2D image. We have one layer, one level we care about, which is basically everything. And here the aspects mask is color, because this could be either color or depth, because like you could have depth or color and so on. Right now we only care about that, and basically this is a slice, which means that you could, let's say, tell it to target the first layer, then the last layer, or so on. Here we have only one layer anyways in one level. And that's basically it. Now let's see if this works. If I haven't forgot anything. I have never written notes while watching the stream, but this is really informational. Thank you. Okay. So GPU presents image, submit command buffers. I believe that's, yeah, one other thing though, is that we need, well, here we could just return okay, which means we're done. Other than that, we need to make sure to basically, so notice here, note that frame index is not the same as image index, right? So the image index is the swap chain image index. The frame index is our in-flight frames that I've explained before. That we just basically prepare frames before while the GPU is working on another frame. So here for the frame index, we're just gonna basically increment it. So like, what is it called? Frame index is equal to self the frame index plus 1 modulo how much frames you have, how much in-flight frames, which is 2. Why? So we're gonna start with 0, then 1. So here we don't have any extra in-flight frames anymore. So we go back and loop again, 0, 1, 0, 1. If we had like 3 in-flight images, then this would be 0, 1, 2. Then we're gonna start again, 0, 1, 2. So basically it's cycling, right? And that's basically it. Now make self-mutable, I believe. Yep, we need to do that. Hopefully that doesn't trigger the borrow checker police. Other than that, we're good, I think. Yeah, I think so. Okay, let's test this and see if this works. Huh. Did we even make a render yet? Well, we're not calling the render function. Okay, so we could call that in the, what is it called? Redraw requested, yeah. So we're gonna say, I guess, self.render, render, whoops, what the heck? Oh yeah, well, we could say if let some if let some render is equal to self.render, well, not take, definitely not, as ref. We don't want to own it, we don't want to take it, we just want to reference here. And you're gonna render, though we're gonna need a mutable reference, so instead of as ref, we're gonna say as mute. And there we go. Though I do remember that maybe you could even do it here somehow. I don't remember though. Maybe like this? Yeah, I remember there was something here, but it was like a long time ago since I programmed Rust, so I don't know. Either way, so this should work. So render.render.inwrap. Yeah. Now let's see if this works. And there we go. You got your first Vulkan window that is just like drawn with red color. That's pretty much it. Well, maybe this could help you with the deprecated functional handling raw display window. Winit has an optional feature. For example, I turned on RWH05 and doing ash plus winit a while ago. I know that RWH, but I don't think. Actually, I don't know. I mean, yeah. Well, we could ask ChatGPT for this. Honestly, we could ask ChatGPT for that. And let's see what we got here, by the way. Oh, what? Oh yeah. Make sure that this is correct, and that should be good to go. Also, one other thing is that we need to wait for, before we destroy the render, or actually the GPU, we need to wait for it to finish any work. Otherwise, it's gonna abruptly destroy the GPU resource while the GPU is working on it, which gonna suck. It could even crash something. First time catching live, what's going on? Hello, Little Gorf, welcome to the live stream. So we're basically making a game engine using Vulkan and Rust, pretty much, using the latest Vulkan features. Vulkan is basically like a modern graphics API. It's like the successor of, what is it called, OpenGL. It's being used by all sorts of games that you play in and so on, like, you know, used by Go.engine and Real Engine. Everything like is powered by Vulkan at this point. Do you use render doc often? So instead of using a game engine, I'm basically creating the game engine, and that's exactly what's going on here. Do you use render doc often? Sometimes, depends. Though it does kind of suck in Wayland for some reason. Working on my own Vulkan engine, any tips? I mean, if you have any questions, please let me know. Though you could watch this stream, it's filled with tips about Vulkan. Pretty much, so that's something. Now, alright, so here we gotta make sure one thing to do, which is to wait idle, device wait idle, before we destroy any resources. My tips I have gathered: dynamic render extension will save you a lot of time in boilerplate. Yeah, dynamic rendering and push descriptors. These two extensions are very, very useful. We haven't used neither of those just yet, because those would require like shaders and so on, which as you can see I didn't do. Right now I'm just clearing the window, and it only took me, using this method, only took me like 400 lines of code, as you can see, which is quite nice. Now let me give ChatGPT this, so hopefully it could help me with the deprecated function. Using Ash or FFI? I'm planning on using FFI. I'm using Ash. Why you're planning to use FFI? That seems weird. Alright, so I'm using Ash, latest Ash version. Alright, let's see what ChatGPT would say. And I'm not sure what's hugging my CPU right now, because it's like its fan's going crazy. Viki config GUI. I'm not sure, sometimes it does that. I don't know why, so let's just shut it down for now, we don't need it. So behind the scenes, the crate still auto implements the all traits for anything that supports, so code continues to compound rest. It's gently shaming us into migration. What do you do? Oh yeah, this is what you said, but not RWH05, I think it's RWH06. So the real actually want is has window handle, which is different part of the shiny new RWH06 feature family. Make sure your window dependency is up to snuff. Alright, so currently we haven't did that. That's why it didn't show us that thing. Because like I was looking for it and I kind of remember a bit about how it works. But apparently I needed this feature. So cargo add winit -- features RWH06, right? Yeah. And there we go. Now, let's see. If I'm right, then I guess with that change, maybe you could even just pass it if I remember, or something like that. Or honestly, I'll just see what's going on here. Okay, let's see how that works. I believe right now we may need to like use has window handle. Something that implements has window handle, I believe. Same thing here. Is that it? But maybe we just need to, but let's just continue our thing here real quick. So implement has window handle, same thing here. I believe implement has display handle, if I remember. And what's next? Expected enum. Now where we're using this, we're using it here. Now we don't need all this crap. I think you could just pass an event loop, as you can see here. And what else? Well, yeah. Okay, cool. Now let's see what's the errors right now. Well, let's see. I believe there's some trait that I guess I have to like add here. So first of all, let's remove the deprecated ones. So I guess only those. Unless maybe if it's maybe needs like RWH05 or something. And okay, so I guess maybe the actual function is just say display handle. Isn't that the case? In wrap. Well, is that it? Okay, so that's how you do it. Alright, cool. Does anyone use Volcano anymore? Seems like Ash won out on the Vulkan API path. There is still people using Volcano. It's actually good. It even have a task graph, which I found really impressive, honestly. It's just that I'm very used at this point to the the raw API. I really don't want to bother learning the whole new API on top of Vulkan and so on. Huge thing now is WGPU. Well, WGPU is a bit different though. So the problem with WGPU is that it also targets web, right? And it targets all these crazy platforms. So you don't get access to a lot of shiny features, even if they're supported on the platform. So basically, even if like your code is running in a desktop, you're still limited to the web limits, right? So basically the problem with cross-platform, in fact not even in GPU stuff, in GPU APIs, is that if you go to a cross-platform API, you're always limited to the common denominator, which means, for example, WGPU can target Android, web, desktop, and so on. Desktop is like the most powerful kind of thing, and web like have a lot of limits. And so even if your code is running on desktop, for example, you can't actually use the desktop features, the modern ones especially. You can only use the web stuff because you're also targeting web. That's the problem with cross-platform APIs like WGPU. So if you're okay with that, then good, just go with WGPU. If you're not, like me for example, and you really care about these modern features and like performance and so on in desktop, then you want something like Volcano, for example. And in fact, Volcano, even they implemented, which even impressed me even more, they implemented ray tracing too. So they have task graph and ray tracing. These are the things they added since the last time I've checked. So that's pretty sick, really. So if you're just starting out in Vulkan, maybe give Volcano a shot if you'd like to. I mean, there is actually some impressive, like if you go to their Discord server, what is it? There's quite a lot of stuff here. Wow. Alright, if you check out the showcase, there is some people actually making some cool stuff with it. Like, for example, there's someone that I've seen actually making a whole thesis. And here's ray tracing. And yeah, someone making a voxel thing, I guess. There we go, ray tracing. Yeah, so it's actually quite good. Mandelbrot set, I guess, probably using compute maybe. And yeah, Nana like LOD generation. So it's really not that bad. It's just that I'm pretty much, I want maximum. Also, if you like want some very modern features, you're limited to Volcano, the features that Volcano implemented. And that's pretty much it. So I think one final thing, well, let's first of all fix this though. Window handle dodge, well, in wrap as raw. There we go. What else? Implement. No, wait, we can't do that, huh? I see. So let's actually remove that. Yep, I can't store that. I mean, I could use dynamic stuff, but no, I need. Rua on the Discord server is very helpful and arguments for using Volcano alone. Oh yeah, I do remember Rua. She's very friendly, very friendly and very helpful. Also Mark, I think. Yeah, I remember I was active a bit on the Discord server back then. I mean, I think years ago. And in fact, it did contribute a little change maybe in the repo. So I do have the contributor role. But yeah, Mark and Rua, very, very helpful people and very friendly. So yeah, if you go to the Vulkan like server, they're very elitist. They're really not helpful. They're just gonna like, I don't know, what is it called? Like they're not friendly, pretty much. They're very not friendly to beginners. But here, Rua and Mark, they're pretty good. They're pretty friendly to beginners. So yeah, maybe if you're starting out with Vulkan and Rust, then maybe try Volcano first. But for me, since I'm already used the raw API and I'm used to it, I just gone straight to Ash. So that's pretty much it. Okay, have you tried Bevy? Definitely. Bevy is pretty cool too. Lovely. I don't know. I don't have too much to say about it. It's pretty good. Like if you want to make a game in Rust, then that's pretty much your best option. The ECS system is like the best in town at this point, pretty much. So yeah, if you want a very good, like, what I really love about game like the Bevy game engine is that's very modular. So like you could, for example, change the render with your own and so on. This is the first thing. Second thing is that if you make your game in the same language that the game engine is in, you could actually step into the game engine code and change it. Like you don't need, or even let's say you're working on like an actual product with a team and you're hiring people with you, then you don't need, like, for example, in Unity, what you could, no, actually, let's say in Real Engine, for example, and maybe you have a scripting language of C#, then you're gonna need basically C# developers and C++ developers. The C++ developers would work on the Unreal Engine on editing it, and the C# ones for, of course, scripting. So that kind of suck, you basically, and you can't step into the code directly, at least not easily. So that's what's nice about Bevy. Like you have one language, Rust, and you could literally step into the engine code and see what's going on and edit it very easily and so on. Finally, biggest pro users of Bevy are not even game companies. That's a sign of... Oh yeah, that's mostly used for simulations and stuff because, well, ECS is very fast, and also the ecosystem about Bevy. That's one thing I also like about Bevy, is the fact that you could like literally check out any Rust library and like just add it and it would work with Bevy, which is like a big freaking plus. Like really, Bevy have quite a big future, honestly. So that's that. Like it's one of my favorite game engines. It's just that it's a little bit verbose and still not as mature as the other engines, especially if you want 3D stuff. And like, of course, especially the tooling and so on. But in the future, I think Bevy would really have a solid position. That's what I gotta say about that. So yeah. Alright, so here's self.display handle. Let's actually remove that and put that here. And in fact, I may actually use it at some point, honestly. I may even cover it and maybe do some tutorials about it, or live streams at least. Create surface. Display handle instance. So let's actually give the display handle here. And like raw display handle in wrap. Though I believe, wait, I think the new one, actually, you could grab the display handle just from the... No? Wait. Nah, that doesn't seem like, for some reason. Alright, fine, let's just go with that then. And not this one. Dot display handle. As raw. There we go. And now let's fix up that thing. Okay, so here I need to give it the window handle. And here the display handle. Oh, I see. Wait a second. Wait a second. Wait a second. Can I just like say plus, I remember? Maybe? Maybe. Tray bound is not satisfied. I think that works. Yeah, I think that works. That's cool. Alright. I believe that works. Let me see. Yeah, it does. Hello, Pranav. Welcome to live stream. And it does. So here I'm basically telling it that I need some object that implements both has window handle and implements also has display handle. And that gives me access to both the display handle and the row handle using one object, which is the window, without having to need the display handle too, which is pretty cool, honestly. That's pretty lovely. So yeah, pretty much. Is there any questions so far? Right now, in fact, we could easily create, like using the smaller kind of architecture, we could create multiple windows here. In fact, like you could have window 2, option window, and render 2, option render. And then what we could do is, are we rendering anything yet? Not really, just like clearing the screen right now, clearing the window, and hopefully next stream we're gonna do some shaders and so on. Create window, window 2, and then we're gonna create a render, a second render. So how are we gonna do that? Well, self.window2 equal window. When would the next stream be? Tomorrow, pretty much, I think. The same time. Convert to option using... Wait, what? Oh, yes, there you go. And now that we got the second window, what we need to do? Well, we also need to create a render, a second render here. Okay, so let's say self.renderer2. Whoops. Self.renderer2, and here we're gonna pass window 2. And for now, we could just share the window size, fine. Because they have the same window size, though you should probably change that. Other than that, we're good. And now, after that, you can say let's some render 2, self.render2, render2.render. How far do you plan on taking this program? I mean, I guess we'll see how it goes. What will your render engine be used for? I'm not sure yet. Right now, I think I'm just gonna make like a generic, not too generic. So like, I basically want to just a little tiny wrapper over Vulkan currently, which I could use to create all sorts of programs basically, without compromising on performance, without hiding Vulkan and so on. So basically kind of like just abstract the boilerplate away, and I still just have some raw Vulkan stuff with a few helpers, essentially. And maybe we could strap in some physics engine like wrap here and so on. And as you can see, also multi-window rendering is also working with with Vulkan pretty good. Lovely. Though we could also take this clear color here, like you could say clear color is basically F32 for, I think. Yep, there we go. And we could say clear color is equal to this. And now, cool project, especially if you can reuse it in multiple. Yeah, exactly. So this is going to be like a library, essentially. Right now it's just an executable, but I want to convert it into a library, which other people could like just pull in like any other crate, and they could use it. So 2 windows mean 2 events loop or no, just 1 event loop for your whole application. And you just create another renderer here, right? So the renderer, as you can see, and only one GPU device. I mean, you could make multiple ones. So the point is why I've shown you here multiple windows is that I'm showing you how this kind of architecture that I basically separated the GPU from the renderer, I could basically make a renderer for each window. So yeah, that's basically the case here, right? And hold on a second, what type expected F32 4 found clear color value. Oh, I see. Wait, clear color. So this is clear color value. And let me show you a little trick here. Nothing crazy so far. We're gonna actually draw some stuff in like tomorrow, in tomorrow's stream. I'm trying to find info on making GUI with Vulkan. Any resource recommendation, or do you have a video or plan on showing that? I'm definitely thinking about covering that, hopefully at some point. Yeah, I'm definitely thinking about that. Just let me know, guys, your ideas, and I'm gonna basically consider them and see how it's gonna go, pretty much. At first, we kind of like basically gonna make this into a little abstraction, so we don't have to like care every time about every single little detail about Vulkan. So we kind of just make this little abstractions. You know, here currently we made this little GPU abstraction that have some helper functions, right? So for example, let's say you want to create a command pool. So instead of writing every time this whole freaking Vulkan code, what you do is just you write GPU create command pool, done. You see? So like basically this could be reused, right? So every time I'm gonna need a command pool, I could just do this instead of every time having to worry about Vulkan. And same thing with the renderer and so on. But yeah, that's basically the plan. And so of course there's going to be a lot of writing of boilerplate code at first, but with time, as we do some extra stuff and we write boilerplate code for it, later on we're not going to need that boilerplate anymore. We're just going to use our own little abstractions, our own little engine, essentially. And of course I'm going to, you know, publish this into GitHub pretty much, and we're going to see where it goes, pretty much. Though one little thing that I'm going to tell you about myself is that I'm very opinionated about the design of my stuff, and I don't care about legacy hardware. So I'm only going to support modern hardware, modern GPUs. So that's that, right? So yeah, otherwise we're good. So here I could basically give, let's say this, some, well, that, all right. 1590 or higher? Nah, just mine and higher. I don't have like a crazy GPU. I like just 3050 pretty much. RTX 3050, 6 gigabyte. Nothing fancy. But yeah. All right. So clear color. But like even like weaker devices, like I mean, as long as they have modern drivers, essentially. So yeah. How about crates? Well, crates not now. It's too early for crates. And as you can see right now, we have two windows being rendered using Vulkan and Rust. One have this color and one have this color by just changing this. There you go. And so yeah, guys, that was it for the stream. If you guys have any questions before we end the stream, and yeah, that was it. In the next stream, hopefully we're gonna look into doing some shaders, and of course rendering a triangle, hopefully. And yeah, so today we didn't even make any use of any kind of like graphics commands just yet. We only used one command, which is cmd clear color image, which is a transfer command, right? Not even graphics. And yeah, just to keep things very simple. I have a lot of questions next stream. Sure, bring it on. So yeah, that was it, guys, for this stream. Thank you so much for watching. Like in a few hours or even minutes, you're gonna find the link down to this repo, to this GitHub repo. There's 72 Vulkan triangulation. No, we're not gonna go that way, because we're gonna be using some modern extensions which would really make things much easier, especially for beginners, and much more flexible, much more performance, basically everything. So yeah, see you guys. See ya, Mucho. See ya, Ryan. Thank you all for coming in, and yeah, goodbye everybody. See you later.